Another little circuit that we can compose is a very fundamental building block that's worth talking about. It's called a multiplexer. So this is one way to implement the multiplexer circuit. And what the multiplexer is doing is it's basically a switch. So we have, in this case, two input values that here we're assuming are single bit values. And we have a select that's going to select between the two. So if the select is 0, that would select x1. If the select is 1, that would select x2. And so either x1 is propagating to f or x2 is propagating to f. And we can express a mux in Verilog with the following syntax. So this is also referred to as a ternary operator. So our output is if the select s, then x1, and actually I guess I said this wrong. So if s is 1, then we're selecting x1. So if s is 1, select x1, otherwise select x2. We can build bigger multiplexers, and there are different syntaxes in Verilog. I think I figured out there are actually 6 different reasonable ways to code a mux. None of them are ideal in all scenarios, but nonetheless we're going to focus on using the ternary operator to express our muxes. So what I've depicted here is we have a select, which is a one-hot vector, which means one of the 4 bits in this vector are going to be asserted. And based on the one that's asserted, you'll select one of the inputs A through D. We can express this 4-input mux as a decomposition using 2-input muxes, so using the picture at the bottom. And with this implementation, I guess the rightmost of the select bits would be the one that gets priority. Meaning if the input vector is incorrectly not one-hot, or we can allow inputs to be not one-hot, and if the rightmost select here is selecting D, that's going to win out over any other selects in the input. Okay, so we can express this lower circuit in Verilog by chaining the ternary operators together. So I guess our select on the right side would be select 0 as I've coded it here. So if we select, oh, and actually these don't match up. So I've actually chained my muxes backwards here. But in my Verilog expression, if my select 0 is asserted, then I'm going to select A. Otherwise, I'm going to select amongst the others. If select 1 is asserted, select B, and so on. And by default, I'll get D, regardless of the select 3. I'm not actually looking at select 3. That D just becomes my default. In terms of how you lay out this logic expression, we can lay it out just relying on the order of operations without the parentheses in the manner I've depicted on the right. These should be equivalent. They look equivalent. And this kind of a layout of your ternary operator, it's really not obvious how to best just format the ternary operator chain together. But this kind of a formatting works out well and is rather readable. So you're going to see this, this sort of syntax in many of our examples. All right, so now we're going to jump into the Makerchip platform. So I'm going to open up Makerchip now. And you can launch the Makerchip IDE, and you can do the same for yourselves. So go ahead yourselves, open up your browser, go to makerchip.com, open up the IDE. But for now, just watch me navigate a little bit through this session. So it comes up by default just with a little bit of a shell for you to code in. So this is TL-Verilog code. I'm not going to worry about the code that's there. In fact, maybe I'll load up an example here. So under tutorials, there's an examples, and let's open up this pipelined FPGA multiplier. Okay, so I loaded that into my editor. All right, and this is my design. It doesn't matter all that much what it is. I just want to show you the platform. But this is generating for us a diagram of the circuit that we're representing in TL-Verilog. And you can split your windows. I'm going to split this top and bottom and put the waveform down below. So the Makerchip platform is sending our design off into the cloud, and it's running our design. It's compiling it, it's running it in simulation. It's returning to us this diagram up here. It's also returning to us a waveform. And you can navigate the design in the waveform. Let's say I notice there's an issue with this signal here, PP3. Right, so I select PP3, and then PP3 is going to highlight here in my diagram as well, so I can see my diagram. I can find where I am. I can hover over these expressions to see the expressions. And if we go to this nav TLV tab, this is a version of our code that we can use for debug, and we can see in this version as well that PP3 is highlighted. And if I click on this line number over here, it's going to take me over to the editor and highlight the same line. And if there's a bug related to this expression, I can fix it. So Makerchip gives you a nice, compact, complete design environment for development through debug. And let's see what else. I showed you pretty much everything. I mean, your starting point when you're working on code, anytime you compile, make sure you're looking at your log. In this case, we have a value that was used but never assigned. And we can go back to our editor and look for line 17 and fix the issue. There are a couple resources in here for TL-Verilog. There's some slides from another course, and maybe I'll add the slides for this course here soon. Paper, you've got documentation for TL-Verilog, specification here. Up here, you can save your work as a new project. Since I haven't saved yet, I don't have anything captured that I can go back to. This will give you a URL that you can then save. I'll go ahead and do it. Yes, I should create a bookmark. So, the saving is kind of primitive. It just gives you a URL. You can capture that in your browser as a bookmark and then return to your work at any time. You can also create clones. So under the project menu, I can clone this. It'll give me a new URL. If you're viewing somebody else's project that you don't own, you won't be able to save that project, so you would clone and edit from there.